meteoroid entering the atmosphere. So let's see what happens when a meteoroid enters the atmosphere. So first of all, we have the object over here in space. In its orbit, it encounters the Earth, and then it starts to push the molecules in front of it, compressing it and increasing the temperature. In the same time, it will ionize the molecules in the atmosphere, and it will generate a cylindrical shock wave that travels in the atmosphere. If we were to zoom in, of course, this is not to scale because the object over here at 1 meter and the column behind it can be more than 1,000 meters. So this is the more or less vacuum because the object travels so fast in a split second, it generates a vacuum behind it. So I will not get into the details because, yeah, it's ongoing. These phenomena are really complex and they're hard to model properly. And the idea is that the object pushes the air in front of it and the temperature can reach more than 10,000 Kelvin. Then it radiates light. So in this process, the object is no longer called a meteoroid, it's called a meteor, or if it's large, it will become a fireball or bolide. Of course, the acoustic waves will travel in the atmosphere and will couple with the ground and can be recorded at infrasound arrays. Then as well, we're going to have a point source explosion if the pressure the object encounters is larger than the tensile strength or the general strength of the material, then the object will fragment and it will cause a catastrophic explosion into the atmosphere. And then, of course, in the rare case, we don't want this to happen, but sometimes they will reach the ground and they will cause a crater due to surface impact. And of course, they will generate a large seismic wave and which will travel on the ground. But what also happens is this spherical shock wave will also couple with the ground and transfer to be recorded at a seismic station. And again, the ablational cylindric shock wave can be detected at a seismic station. So as you can see, this phenomena in the atmosphere is quite complex, and we can use several tools to analyze it. Why is this important? So first of all, the meteoroid mass scale is quite uncertain. When we get to this meter-sized object, it's really hard to detect them before they enter the atmosphere. So the size scale is not very well constrained. And even if we were to detect them at that size limit, it's a hard problem to solve. So what also happens is if we have an object that leaves meteorites on the ground, so we have the meteoroid in space, the meteor when it ablates in the atmosphere, and then the fragments on the ground are called meteorites. So these, when we study them in the lab, they're like a history book of the early solar system. These impacts are also analogs for larger objects. So by studying these objects that are very common, fireballs, meter scale objects enter the atmosphere at a weekly basis. By studying them, we can these provide analogous data to larger objects. And then by constraining their side flux density, it's really important for spacecraft shielding because when we go to small sizes, they are very, very common. And these pose an impact to spacecraft. And of course, the solution would be to use multi-sensor simultaneous observations, having the atmosphere as the detector. But going back to space, let's see what happens when these are some of the images of impacts onto spacecraft. And over here, it's an impact that hit a coolant device in the Soyuz spacecraft where astronauts are inside. And this is a major impact on one of the mirrors of James Webb. And of course, they can also hit the astronaut suit and cause it to leak. So these are important to constrain. When we look at the size of objects that hit, um, objects really small, 10 to the minus 5 grams, they pose no damage because they are so small that they decelerate upon impact without causing much harm. They would just cause a small dent in the spacecraft. But when you go to larger objects, about 1 millimeter, 1 millimeter object traveling at tens of kilometers per second, they can pierce through the spacecraft and then it will damage the equipment inside. And of course, we have the 5 centimeter range. It will just destroy the whole equipment. So these objects over here, we see them as visual meteors. So we see them visually, also like shooting stars. And the bigger they are, the less likely they are to encounter anything because there are very few. For this, we have different devices, different networks. For example, this one is the Freepon network, which covers most of Europe. We have here a zoom in on the Romanian network. The idea started about 10 years ago, and the first camera was installed in 2015 over here at the Paris Observatory. And then it expanded throughout France, and we also adopted it in Romania. For now, we have about 240 installed stations, and many countries are increasing their number of cameras. For example, right now, Chile, just in the past few months, they installed about 10 more cameras. So Chile is quite a good spot for observations. But since we're studying large objects, so fireballs, these are also good in big cities like Paris over here, or Bucharest. We have here one Bucharest at the Astronomical Institute of the Romanian Academy. So all the cameras are all sky. So they see the whole sky in one image. And this is this is a good way to cover a large surface area when you're studying large objects. Because when you're focused on faint meteors, then you need narrow field cameras to observe a bit with a bit more signal to noise ratio, the small objects. So the project in Romania started in 2016, and this started right after a large. It started the first setup was in 2016 after a large object at the beginning of in 2015. This was in the Romanian Super Bolide. It was a really large object that impacted around the middle of the country. At that time, we didn't have any network to observe it, and we used the cameras coming from the security in security spots or the amateur cameras to triangulate. Then we decided to expand this network, and right now we can reconstruct the trajectory. So by having several cameras, we can observe the location of the object and then triangulate to reconstruct the trajectory in space. We can measure the mass, so the luminosity of the object. What we can also do is track it back in the solar system to see where the object is coming from, and then associate it with a possible parent body. Then what we can also do is we project where the fragments might land. So if we have it the trajectory in the atmosphere, then when it extinguishes, so when the ablation is no longer sufficient to radiate light, the object continues in the atmosphere and it will continue to fall to the ground. And then we can estimate also the location of these fragments and go on the field and search for the meteorite. So this is the dark flight and the strong field. And the next objectives would be to expand the network, because this is right now it covers more than 60%, but we plan to expand it more to cover some other spots as well, and then enlarge the search teams, because we need to go on the field and search for the meteorite to study them in the lab. Going back to the larger consortium, the FRIPON, all the data is open access. Yeah, we can get on this website and observe the objects that entered the atmosphere this past night. And the network is currently expanding. This is a zoom in on the European coverage right now. And what these observed impacts for the past 10 years, more, and depending on when the stations were installed, the objects were more observed or less. So, for example, if we overplot the distribution of objects that were observed entering the atmosphere, so distribution of fireballs, you can see a very cool trend here in France, because northern France doesn't have that many clear nights. And when you look at southern France, of course, you get a better weather, and then you see a larger number of impacts that were detected. One interesting object entered the atmosphere over here in southern France. So it was the covered night at the Hendaye here. And what you can see straight away is that, the object entered the atmosphere and crossed from France to Spain. Over here is the border at the Pyrenean mountain range. And it was observed from Hendaye and Dac through the layer of clouds. But and from these two stations and the one on Mont Sec, we could reconstruct the trajectory, and we know that the object entered the atmosphere at 87 and ended the radiated light trajectory at 26 kilometers. There were teams on the ground over here, but they could not find any meteorites. So a large part of the work is to search for the meteorites, but sometimes the fragments are either too small or the ground is not very permissive for searching, meaning high grass. So from these, we could estimate the impact energy. This can be done by several methods. For example, the dynamic method is to accurately track the trajectory and understand how the object slows down. And of course, the larger it is and the more surface area it has, it can go further into the atmosphere. So by slowing down, how efficiently it is, the slowing down effect, then we can estimate the impact energy and the object's mass. Another method would be through acoustic seismic coupling. So the object produced an air wave, which also can couple with the ground and was detected at several seismic stations of the Spanish seismic network over here. And this provides an independent method of measuring the impact energy. Another method is through infrasound, and the infrasound traveled through the atmosphere over the Mediterranean and was detected at the Tunisia CTBTO station. And this was more than 1,000 kilometers away. And then infrasound provides an independent method of measuring the impact energy. And of course, we have the radiated light, and this is done by integrating the light curve. And this provides an independent method of measuring the impact energy. So by putting it all together, we have an idea of what happened in the atmosphere, and we can cross-calibrate. So one idea to see how well these objects are, the parameters are constrained, is to look at previous impacts which had meteorite recovered. So this is the list of the impacts of the fireballs which had also the meteorite recovery campaigns which were successful. So we have also the laboratory analysis, and we know the density of the object, which provided further data for the trajectory modeling. So by looking at this, we kept only those with a published light curve, because what we wanted to do is to find a better method to estimate the impact energy, and the light curve provides the the light curve is um, the most common reported measurement of the object, because you can see it in the atmosphere. You have the recordings of it. You can measure the light, and then from this measurement, you can also derive the trajectory. So the light curve is the most reported measurement of the object. So we decided to have a better look on that. And from this, we looked at objects which correspond to decimeter scale meteoroids, so below 1 meter, because if we have larger objects, they fragment, they have free internal cracks, they are more likely to fragment in a particular way. And we decided to look on the smaller objects, less than 1 meter, to see how the light curve behaves in the atmosphere. So the idea would be to obtain the radiated light, because some of them, they only have the light curve published, but they do not have a sort of method to estimate. They do not have a integrated light curve in an energy format. So to do that, for example, we have here the Creston bolide in California. So Peter Jenskens reported in the paper the light curve, but there was not a method there was not an integrated light measurement. So what we did is we digitized this, and by digitizing it and integrating it, we can plug it into this formula that assumes that an object of 0 magnitude produces 1500 watts. So this 0 magnitude star produces a 1500 watt, and an object this corresponds to an object at 100-kilometer range. And by digitizing the light curve, we obtain an integral of 1.7 times 10 to the 9 joules, which can be converted into tons of TNT. This is a common method of reporting the impact energy. And the idea would be to obtain the radiated light for the others that did not have it reported in the paper. So some of them, they report the radiated light in ergs, which can be converted into joules and tons of TNT. And some of them, they give it into tons of TNT straightforward, and we obtained it from there. And some of them, we had to convert it from joules. But for most of them, we had to digitize their light curves and extract it from there. So this is their reported light curve, and we obtain an estimate of impact energy of the object. Now, when we put it all together, we have here the column with the optical energy. This is the radiated light during the descent. We also have the velocity and the mass. So the velocity is and the masses are reported in the paper. So we take it as is from the paper, and they also have an error associated to it. This is because they have different methods and independent methods of estimating the mass, the pre-entry mass, and they give a range of values that they found to be very relevant to this measurement. So uncertainty is associated to it. Over here, we also included 3 objects detected by European network. And these are very fast ones, because you can see over here the velocity, but the particular element of this is that these were observed by cameras. The airwave was detected at infrasound stations, and also the shock wave hit the ground, and they provided an independent method to measure the impact energy via seismic processing. So usually when we look at the objects that leave meteorites, they are quite small, they are quite slow. They are between 12 and 20 kilometers per second. You can see over here the velocities, because otherwise they will just destroy in the atmosphere, like these over here did. So these do not have meteorite recoveries, but we had different methods of estimating their impact energy, because they were quite they're quite well observed. So when we put it all together, we have the mass and the velocity. We get the kinetic energy, which is displayed over here. Now, when we plot the source energy versus the optical energy, we obtain a fit over here. And these are the list of objects that were studied. And by this fit, this provides a relation of associating the optical energy with the source energy. So when we look at the previous one by Brown about 20 years ago, they had one, but they're stopped at about 10 to the minus 3 kilotons. We provide one over here that appears to be that smaller objects are more efficient in radiating energy. And this is one of our findings. So right now, when we have the energy radiated and measured of an object, we can plug it in here into this equation. This is derived from the fit. And this relation provides an empirical way to measure the impact energy. And now when we have the impact energy, we can replug it into the kinetic energy formula to obtain the mass, because we have the velocity already measured. So this is one method to measure the impact energy. Now, when we put it all together for this Pyrenean fireball, what we observe is that through dynamic means, we get a fairly large error bar, and sometimes it can go to over here, which this line is 100% efficiency. That means it can go to unphysical errors. Now, when we have the seismic method, provided a very large measurement, but the lower bound of source energy intersected the ones that we obtain from the radiated light. And infrasound, unfortunately, we have only one infrasound station, but we know that when we go to energies lower than 1 kiloton of the impactor, the infrasound method does not provide a reliable method of measurement of the impact energy. And this is one possible explanation of this outlier over here. And it's very dependent on the wind speed, wind velocity, and and the atmospheric conditions. So for the infrasound method to work, we need many stations to observe it, but we only found the detection on one. And now when you look at the radiation, with the associated error, we see that is the most constrained and reliable method of estimated impact energy based on the previous methods, based on the previous impacts. Now, since then, there are other objects that have entered the atmosphere. So over here, we have the Cavezzo meteorite, which entered the atmosphere on the 1st of January, 2020. So for a while, it was called the New Year meteorite. And the funny story about this one is that the Prisma network in Italy, they send very fast the news out for people to look out for objects in this area. And a man took his dog and they went on the field and they to do the morning walk, and then the dog found something really, really strange and was attracted by the smell of the meteorite. And actually the dog found this meteorite and pointed to the owner. And it was a funny story. And then many people went on the field over there to search for some, but only these two fragments were found by the dog and his owner, because the owner remembered that there was a fireball the previous night, and they contacted the team. Another one since then was the Winchcombe meteorite. This is the object is quite rare because it's carbonaceous chondrite, and these are quite soft. that's why on our meteorite records on the whole world, we have only 4% of them are of the type are carbonaceous chondrite. And the idea is that these have very low density, are quite porous, and then are soft. And when they enter the atmosphere, not much of the material survives. When you see them over here, it impacted the ground, the alley, at the house, and the owners thought that this was a joke played by the neighbors throwing charcoal from the barbecue in their on their walkway, and they didn't know what was that because it looks more like charcoal than the rock. So although we have more than 80,000 meteorites on our collections around the Earth, only 4% of these type are carbonaceous chondrites. It should be about 50% because when we look into the solar system, we see that about 50% are objects of C-type, so carbonaceous chondrite sources. And but when we look at our meteorite records, we see that only 4% of them are these type. And we found out recently that these objects are very likely to be destroyed also by planetary collisions and also by heating due to perihelion passages close to the sun. So this provided a very since this object was obtained about one day, a few less than one day after it collapsed and after it entered the atmosphere. The many teams around the UK got to analyze this, and this provided a very fresh case of carbonaceous chondrite studied in the lab. One of this provided this is more like a space mission sample return than a meteorite recovery. Another one since then, in British Columbia, in Canada, the object entered the atmosphere over Canada, and very interestingly, it entered through the roof of a house, and it collapsed into the pillow of a woman which was sleeping next to it. But what the woman reported is that she usually sleeps on this area of the bed, but for some reason, for this night, she moved on the right side of the bed, and this is when the object entered the atmosphere and then went straight to the roof of the house. This is the roof of the house, and then through her bedroom and on the pillow. And it was recovered also quite fast. But this this is the first occurrence of this nature. Another one quite recent in northern France. So the object was detected about 7 hours before impact by Christian Zarnecki. And at that time, people thought, okay, this is an asteroid really close to the Earth. And then he reported observation, and then several others observed it. And then JPL computed trajectory. And the idea that it was going to enter the Earth's atmosphere. So many observers start to observe it at that time. And the area was constrained to northern France. So it was quite important to get as many observations as possible. And this one was observed at this observation is from the Astronomical Institute of the Romanian Academy. And you see the object over here going around a circle. And this is because during these observations, the object was coming close to the Earth, and the Earth was rotating during these hours. And that's why the object appears to rotate in the sky, because you have the parallax effect. during the hours of observation. So I have this sometimes bad habit of reading my emails just before going to bed or coming back home in, during the evening. And I observed this alert. And at that time, I was in Paris. So when I observed this alert, I set my alarm clock to wake me up just before the object entry because I thought, okay, since it will enter the atmosphere in Normandy, I might be able to observe it from Paris if I look towards the direction. So I put my alarm clock to wake me up about 10 minutes before the entry. Okay, when I woke up, I checked again, and the error was down to 0.2 seconds. This is the error of object entering the atmosphere. So 1 hour before entering the atmosphere, the error was 1 second, and 20 minutes before, this was 3 UT, 4 a.m. Paris time. This was February, 13th of February. 4 a.m. Paris time, the error of impacting the atmosphere was 0.2 seconds. Quite well constrained because more observations have led to better constraining the impact time. So I went outside. I took my laptop, opened the webcam to record the event. I also put my phone towards that direction, general direction of the impact, and then started the recording. And then this is what I saw. I saw the object entering the atmosphere. And it was recorded. This one was recorded with my laptop. For some reason, my phone did not focus well because it was pitch black, and it was not a sort of a. It's not designed to take these videos, but this recording proved really well to obtain the radiated light. So the next day we put all the data together. This was the prediction by JPL of the impact. So this is the England over here, you have northern France, you have Normandy over here. The problem is we did not have the trajectory quite yet because it takes some time to process everything and together to calibrate observations. And we knew that object fragmented in the atmosphere, but we didn't know where. It could be at 40 kilometers, this is above the sea, and it can be at 20 kilometers above the land. And in terms of searching for meteorites, it's really important to be above the land and not above the sea. Because if you want to search for meteorites in the sea, you have all these rocks on the beach. You have all these rocks. This is very characteristic of Normandy because you have rocks that are breaking down from the coast. So this is not a very a very good meteorite search area. We put all the data together. So during entry, the object, we know that it fragmented, and this is the location of the stations, and we could triangulate the trajectory. We know that the object entered the atmosphere at 100 kilometers, and then it had this major disruption at 29, and the light stopped at about 19 kilometers. And the one interesting aspect is that the object was detected by observers over here in Normandy. And I don't know if you could. I'm just gonna stop this. So, okay, can you hear me right now?
Yes, we can hear you.
Okay. Because I put it on direct. If you could hear the audio, let's see.
Wow.
You could hear something?
Yes, some people in the background.
This was but the I don't know if this is okay.
Wow. these are the parents of one of my colleagues, which were over there in Normandy, woke up at 4 a.m. just to observe it, and they were quite enthusiastic about it. But from this video, we could recover several fragments as the object ablated larger and larger particles in the atmosphere. So we have 9 individual fragments detected, and this provided the best estimate under the object. It was also observed by a colleague over here in Paris. So this is another video from Paris by Ruslan. And the first day we went on the field and we found the meteorite. This was a student at that time. She was at high school. She was 18 and she wanted to join the search campaign. And this was the first meteorite which was found from this fall. Of course, everyone had a party at that time because we had the object less than a day after the fall, and was quite important to get it into the lab and to analyze the particle, the gases that are and the elements that are altered in the object due to the atmosphere and the humidity. So it's really important once we have a meteorite to send it really fast to the lab if it's after a fall, because it will preserve some of the memory of the solar system more than after altering. The days that followed, several other people joined. So more and more fragments were found by volunteers. And what we can see over here that we had more than 100 meteorites were found on this strewn field. What was really interesting, this is an early image of the fragments. These go over a small town. And of course, we had to search on the field because people are quite skeptical when you ask them to search in their backyard for meteorites. I don't know why. So on the field, it's quite okay, nobody bothers you, and you ask for permission for the mayor and the owners, and they are quite happy to give us. The search continued. This is more or less how the area looks like. Over here, we search for the largest piece because as the object broke into the atmosphere, it left many small pieces, but there was also a larger piece which we think it's more than 1 kilogram. And this is how the search looks like. So you get on the field, you have different types of environment, and you walk and you search for hours and hours. And depending on how the ground looks like, you stop every now and then. For example, for this one, this looks like a meteorite. So you sometimes stop to see, okay, this is a meteorite or not. What's very strange about, and the particular special about northern France and Normandy area is that you have this rock, it's called silex, and it looks like meteorites. So we have to stop every now and then to decide if this is a meteorite or not. So this was quite challenging, to say the least. Now, when we put it all together, we have the object observed before entry, we have the atmospheric trajectory, and we have the entry mass and the trajectory reconstructed, and we published this about 2 months ago. One important aspect of this impact is that the object is an L chondrite, and L chondrites, this was the second instance of this such impact, is that the object entered the atmosphere, it kept most of its mass until it exploded. So it carried the energy really down into the atmosphere and generated a shock wave, which was detected at many seismic stations and infrasound stations. And the idea is that, okay, if we have this type of object that we see that is bound towards the Earth, so with coming from a L-type source, it might have catastrophic consequences, meaning that the object can be really strong and it can fragment really low into the atmosphere to generate a shock wave. Another one was a more recent one. This was discovered also by Cristian Sarnecki and was observed by the Romanian Academy, is that this one was detected just 3 hours before the impact. They sent the alerts, we could observe it and reconstruct the trajectory. We have over here the atmospheric entry. And this entered the atmosphere in northern Germany near Berlin. We have Berlin over here in really close, and was observed by several stations around it. So this is the closest video, and we see different fragments that were ablated from the object. And what was really interesting about this one is that it had a high inclination from the horizontal. That means that the strewn field, the location where the fragments land, it's quite well constrained over here. Because if it were to be tangential, like this, the fragments would have landed on a larger area, possibly hitting some of the locations in Berlin. But the idea is that since the location was, the entry angle was quite steep, the fragments landed in a narrow region next to Berlin. Of course, this was not a large object, but the fragments might have landed in a wider area due to a change in entry angle. So by putting all the data together, we derived an entry mass of 140 kilogram, and this is the smallest object observed in space so far, because most of them are meter or kilometer scale objects, but this is the smallest one observed so far, just because it was heading towards the Earth. And when we look at the strewn field, if we were to model without the wind, so not taking the wind into account, we would have over here the about 1 kilogram. No, this is the 1 gram objects, 10 gram, 100 grams, and this would be the 400 gram objects. But if we add the wind into the mix, the wind shifted the location like this. So the 1 gram fragments were shifted all the way over here, and the 400 grams are affected less by wind, and they are shifted just by a small amount. But the smallest fragments are affected most by wind. So this was the object took the name of Rübeck because over here is the location of the first fragment found. And this is a quite interesting meteorite because less than 1% of our finds are like this, less than 0.5%. This is an albright, and we actually don't know where these objects coming from. We have some ideas, but we do not know. And of course, they put it at the Museum of Natural History in Berlin. Now, when we go back to this plot, we add the new data, and we see that our previous method that estimate the impact energy based on luminosity, when we add the new data, it fits quite well. And not only on this area that we constrained, but also when extrapolated to smaller energies. Over here we have one Arpuquilpu that has no data, is not that well constrained, but is this one is from Australia. And to larger objects as well, it can predict quite well the impact energy based on the radiated light. So this was presented recently at EPSC in the poster. And the main conclusions are that the bolide radiation is the most reliable method of estimating the source energy of large impactors. The new well-calibrated events that occurred in the past few years hold when plotted against our relation. This is regardless of the impact energy deposition profile, because some object they fragment early, some object fragment late, some object fragment only once, and some fragment many times. But doesn't matter where they fragment. Our method stands for we found that the relation stands regardless of the fragmentation profile. And this method would be applied to analyze the size frequency distribution of impactors when by calibrating the observing time and the area covered and the detection limit. And this will help to calibrate other tools like infrasound and seismic for objects at this scale, because infrasound is calibrated for larger objects, kilotons, but for these that are very common and more frequent, infrasound needs to be calibrated because the infrasound networks cover the whole Earth, while the fireball networks cover just part of it, and radar measurements as well. Thank you very much.
Thank you, Simon. That was very interesting and visually also very pleasing to look at. We had a question when you talked about the Freeton network, and Omar wanted to ask what's the process of adding to the open access database, and can anyone add there, or is there some vetting?
Okay, so the open database is directly connected to our results. So it is this open database is a consequence of our detections within the network, within the cameras like this. If you are to add to that database, it's not possible through other equipment than to join the network. But what we also there is also global database which is linked to the IAU, so International Astronomical Union Meteor Data Center, and there is where people publish all the data from different networks, and we can analyze it collectively in an open format. So one idea to contribute is through the International Astronomical Union, MDC.
Okay, thank you. Does anyone else have a question?
Yes, I have a question.
Hello, Anya.
Hi. I have a question because all of the very fast impactors, but by the way, really great talk and great project. I really liked it. So back to my question. All of the very fast impactors that you discussed were from the 2001, 2004, if I remember. Is there a database of those of newer one of those very fast ones, or why there aren't recent observations of those?
Yeah. So this
not included in the...
Yeah, these were the ones that I could find in the literature that also had different independent methods, because there are many of them in the literature and in databases, but they only report only one type of measurement of the impact. So they report either through photometric mass, and that's it. They report the dynamical mass, and that's it. But these three were published in the paper, which explored three different methods, because these had very well calibrated radiated light through radiometers. The signal was detected at infrasound stations and seismic stations. So they provided different methods to constrain this mass, this pre-entry mass. But of course, next idea would be to have several methods of estimating the impact energy for large speed object as well, high velocity object.
Thank you.
Yeah, thank you, Anya. Does anybody else also have a question? Okay. It maybe seems not, and we also are coming to an end of the seminar. I don't know if Simon wants to say anything else, but I think you can answer any questions if anybody else has later by email or something.
Yeah, I think my email is on the list right now.
Yeah.
Mhm.
And thank you again for a very great talk. It was very interesting.
Thank you, Alexandra. Thank you, everyone.
Okay, I wish everybody a nice day.
Have a nice day, everyone.
Thank you again. Awesome talk, and bye.
Bye-bye.
Bye.